All right, here we go. Now, so again, if you see this on, that means that we're recording for all posterity. Liquids possess low compressibility, lack rigidity, and have high density compared with gases. That makes sense because the big property of gases is these particles are so far apart and they're moving at such a high rate of speed. They've got a lot of energy. They're not interacting with each other. That's the point of gases. Okay? We have these definitions. Remember, we should have gone through our chapters and looked at surface tension, at these purple words like surface tension, the resistance of a liquid to increase its surface area. That's the cohesive ability. Things like water have a, you can have the bubble across the top of the tube. Have y'all done that before? Where you just keep adding water and water until it actually creeps up and over.
Yeah.
Okay? Or whenever we measure things in a graduated cylinder, we look at the meniscus. And the reason for that is the attractiveness of the water to the glass and in of itself, and that's why it creates that curve. So that's why you want to measure there. Because even though it looks like it's a lot of water, it's just a few molecules up against the edge. And so most of them are on that surface there. So you need to know that definition. We'll talk about it. Polar liquids exhibit capillary action. So one of the things we talked about early on is things like chromatography, and specifically paper chromatography. It's one of our the very early chapters. About every other year or so, it seems like there's a nice question on chromatography on the exam. So you're going to want to check out those questions. Capillary action has to do with cohesive forces and adhesive forces. So cohesive, right? How much they stick together, and adhesive, how much it sticks to something else. So you can think about those little sticky notes. They have both cohesive and adhesive properties. It tends to be more cohesive. It's going to stick to itself and stick to the paper more than it will stick to some other surface. So you can have that. But here's what's going on. Your adhesive forces is your water, for instance, with the meniscus there sticking to the walls of the glass tube. There we go. That's what we're talking about right here. So you can zoom in here and you can actually see the adhesive forces of the glass are stronger than the cohesive forces in the liquid. This is being stuck here. It can pull some of the atoms up here, some of the molecules in interaction with the polar glass, but not a whole bunch because of the width of this, the weight of these water molecules pulling down. Only a select portion of molecules are going to be stuck to the glass here. And that's going to create this little curve. Okay? Something like nonpolar mercury, if you've ever looked at a mercury thermometer, it has a curve like this. And it doesn't like being in the glass because it's nonpolar. The glass is polar, so you actually, if you zoom in, you see this little separation here. This is useful for things like thermometer because it's just sliding up and down the tube. The glass is just holding it. It's not actually interacting with it. You wouldn't want to use water. Okay? So viscosity is a measure of a liquid's resistance to flow. And if you have large intermolecular forces and complex liquids, they can be highly viscous. So your greases, they don't flow very well. So that's why you don't take, after you've cooked 4 or 5 pounds of bacon, you don't take that and just pour that down the sink. You do not, because it clogs your sink, right? It's viscous. Now, when it's warm, it's not, because you've excited it, you've broken those intermolecular forces. That's why it's liquid. But those London dispersion forces come into play as it cools down and becomes a cooler and cooler liquid until it finally becomes a solid. And of course, you don't want that solid in your pipes. Okay, you'd rather them in your arteries. Okay, all right. That's good stuff, right? You got to be careful about that. What's that?
Is it for sure?
For sure, yeah. You pour it in your coffee can and you use it to cook with later. What? That's wasteful. Or when you make green beans, you pour it in there. It flavors the green beans up good.
Ew.
Y'all never eaten bacon-flavored green beans?
Who likes green beans? You guys are so good.
Sounds interesting.
Yeah. All right. So here's what's going on with liquids. We've talked about solids. We know how they tend to arrange themselves. And of course, gases we know tend to be so far apart from each other that they don't really have any arrangement. There's no interactions. But they have strong intermolecular forces, but they also have significant molecular motion. So they're that in between. If you remember, I told you the phase of something has to do with this war between the kinetic energy and the intermolecular forces. So if I have very high kinetic energy, I can overcome any intermolecular forces. But if I have a moderate amount of energy, like say 25 degrees Celsius, then the intermolecular forces come into play. And so things that are solid, intermolecular forces are winning. Things that are a gas, the kinetic forces are winning. Our kinetic energy forces are winning. And the stuff that's in between, the liquids, they're in between. That's what we're talking about here. They are still in a similar arrangement. So if we think about water, I've still got a lot of hydrogen bonds, but I've also had a lot of broken hydrogen bonds. So some of them are together, some of them are not, and they're forming and breaking all the time. There's usually some holes and some regions subject to fluctuations. Should make sense. Again, using the analogy of you guys in the hallway, there's points in time when there's a big gap between you, and then not so much now that our school's so small, but you know, some of y'all remember last year, even 2 years ago, when you could barely get down hallways because we had 4,000 kids here. Yeah, little flashbacks. But yeah, not so bad now with the, a third of the kids gone, and then of course we're already smaller. So, all right, so let's take two liquids. I've got A and B. I've got liquid A exhibiting stronger intermolecular forces. What are some of the following statements that are true? So I've got two, and I've got two on the next slide. So decide if A is true and write it down, and then B is true, and then we'll flip to the other ones. So A is going to have stronger intermolecular forces than B. Is the surface tension and viscosity of A greater than B? Mm-hmm. Is the surface tension of A greater than B and the viscosity of B greater than A?
No.
Okay, let's take a look at this one. Is the surface tension of B greater than A and the viscosity of A greater than B? How about the last one? The surface tension and viscosity of B greater than A? No. Okay. So we all agree that it's A, right? Good. All right. So we have a couple of things going on. Yes?
Can you explain that, please?
Sure. All right. So I got, if liquid A has a stronger intermolecular forces, in other words, the attraction between the particles are stronger, it's going to be solid at a lower temperature, or a higher temperature it'll be solid. The one that's stronger. Okay, it's going to take more energy to move it into a liquid phase. It's going to take more energy to move it into a gas phase. Because it's stronger, it's going to be more resistant to flowing because it wants to stick to its buddy, who also wants to stick to its buddy, who wants to stick to its buddy. These guys are all sticking together. They're not going to flow well. So if they don't flow well, it's got a high viscosity. All right, so I've got amorphous solids and crystalline solids. Amorphous solids have a lot of disorder. Crystalline solids are a regular arrangement. Those are really the two different types. And then within crystalline structures, we've got lattice. You've heard lattice before. What's that?
The energy
Well, that's lattice energy. Or ionic compounds form in a crystal lattice. Crystal lattice. A three-dimensional system of points designating positions of components that make up a substance. All right, this is what we're talking about. This is not unique to ionic compounds. You're going to have these repeating things. So if I have sodium chloride, I have a crystal lattice of sodium and chlorine and sodium and chloride repeating, right? And the smallest repeating unit of a lattice is called a unit cell. Right? because we read our chapters and we're good. And we did our reading guide. You're okay. You're the one person who's excused.
So, how would you determine a high viscosity liquid from an amorphous solid?
It's a good question.
You probably don't know.
Good question. It'd have to be very high viscosity. So here's some different types of, yes?
I was just going to ask him exactly the same.
Okay. So these notes here tend to follow real tightly with the notes I just gave you.
He's lying. No, they don't. I was just running with the fun.
Good, good.
They don't follow.
They're out of order, but they're there.
No.
They're there.
See, it's right there.
But it can be really inconvenient when you're talking about something else. It's like
Crystalline
where's
solids,
it?
amorphous solids.
Yeah, okay.
But you read the chapter, and so you've already memorized all these purple words.
No one has read that.
Why not? Yeah, go ahead.
You got enough class? I didn't think we were learning more.
You always learn more.
No.
This is chemistry. You
Come
want
on,
to
you
learn
know.
more.
This is chemistry. We always learn more. You're right. Every day is a review of everything you've ever learned.
I used to think this was Latisse. Like, that's why I used to think
Latisse?
So, no, this is not a review.
All right, now it's lattice. All right, so here's some options we have. We have a simple cubic. Some of you probably remember. We have a body-centered cubic. Okay? So there's one in the middle. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. This one we just have the 8. And then we have a face-centered cubic. All right? And this is going to have one in the middle of every face on the cube. Yes?
When's our test? Not Friday.
Yes, Friday.
Today's Wednesday.
Today is Wednesday.
So next
Why do we
class.
have?
Yes.
Can I take it like Monday or something?
Yeah, you and I will talk. We'll figure that out. And you too. So you've been gone a while. So. No. All right. If you expand these unit cells, this is what they look like. They're going to repeat. If you'll notice in the face-centered, each face is shared between two adjacent ones. All right. And these pictures are also in your textbook. If you were to do a space-filled model instead of the ball and stick and actually slice them, you could actually see that I've got each corner is not one, but is because it's adjacent to the next cells, right? So they've been cut like that. Okay. This uranium has one entire atom and then 8 partials. And this one, each face has a half, and then each corner again. Okay? So this is polonium and uranium and gold. Looked at aluminum the other day when we did that little aluminum lab. Okay? Aluminum looks like this. So you can think about the amount of empty space between the atoms. It's fairly minimal when you look at the density. How many of y'all got density calculations? Pull out your aluminum lab, see what you got.
I made a mixed division. So I actually tried to round number.
Lots of different ways to solve for that. I just want to see who got somewhat close to right answer. Yeah, the final question was calculate the density.
1.5 times 10 to the negative 7 grams per cubic picometer.
I would have to do the math and see. Okay, what'd you get?
That's the same thing?
What'd you get?
We got, the first time we did it, we got 1.2 grams
Grams per
per liter.
liter. Okay, that's not quite.
Wait,
I don't know because I wouldn't have done it per picometer. So typically we do it by grams per milliliter or grams per centimeter cubed.
I don't know how to convert that.
Yeah, so you need to convert that for me, then I could tell you. Because picometer is times 10 to the what? Negative 12
What? What's 9?
nano
Oh, that's
nanometer.
And micro is -6, right?
Yes,
I made a strong last.
there you go.
You did.
All right, so the real answer is about 2.7 grams per centimeters cubed.
Okay, we might have been close.
Yeah, it could be.
Maybe.
There you go.
Close, actually. Just take away some.
So a lot of people got reasonably close trying all kinds of different methods, so that was pretty good. One that I hadn't seen done before, so it tends to work. All right, let's take a look at X-ray analysis of solids. This is one of the things that was we do this in the lab when we're trying to find out what the structure of proteins are. We do what's called X-ray crystallography. We take the proteins, we form crystals. We then actually create a, yes?
I have a request.
Uh-huh.
Can we go back to the note packet we had last year with the smiley faces on it? And
No,
then
there's no
the
smiling.
Oh,
There's
the
no-
blank.
There,
Yeah,
there's no smiling in AP chemistry.
Okay, I stopped
okay,
it.
no smiley faces, but all the blank notes. Help me
Yeah,
out.
okay, but what we're trying to do is move you to your college. This is a college level course. And even now, that's really far more notes. Typically, they're just going to hand you I'm not going to hand you, you're going to go buy notebook paper and you're going to take notes in class and read the textbook.
Okay, I'm part of this.
Good? All right, cool. And we're going to take some pictures. We're basically going to shoot X-rays at them. They're going to hit the crystals and they're going to bounce in certain different ways. They're going to create patterns where they're going to interpret those patterns. So then we're going to go in the proteins, we're going to change one amino acid. And we're going to take another picture, see what happens, see what changes, see what the structure changes. And we're going to say, well, by changing this amino acid, this opening opens up more, or it shifts, or it does something different. And so I can say that that amino acid is really important. Or I did this, I changed the amino acid, and really nothing changed. The structure is about the same. Okay? And so we're not going to dig too much into that. This is what's going on with diffraction. Okay, so it reflects. And if I have something different, you can actually compare the differences here. And we can use the Bragg equation. I don't expect you're going to have to know this. Where'd it go? There we go. So this is not something you need to memorize. We're just going to point out how it's used. And we're going to use a little bit of trig. Y'all enjoy trig. So I know everybody's in pre-cal or trig.
We just did true.
Yeah, okay, that's right. We just finished. Yeah.
Yeah.
So, okay.
Wait, you just did the trig? There's no just doing trig. It takes like the rest of the semester.
So I think y'all they do trig and then pre-cal.
It's like first semester.
Oh.
Yeah, we did
pre-cal
trig.
first semester.
No,
Oh.
that was trig.
DC?
Yeah.
Yeah.
Yeah, I'm pretty sure it's trig and then pre-cal.
Yeah.
And then honors is pre-cal and then trig. At least it was. I don't know if they still do it that way. What'd you work on? What'd you do last semester? Pre-cal or trig? Okay. All right, so here we go. There's our Bragg's equation. And then, again, I'm not going to ask you. I may have to throw you a homework problem or two, but it's not going to be on the test. I just want you to think about how X-rays work and how X-ray crystallography works. So think about that. Used to conduct X-ray analysis of crystals, we can rotate the crystal and then get some data. That lets us talk about bond lengths and angles. So we know things. We know, for instance, we know that these stick models, that bonds are not rigid like this. They don't sit here like the sticks. These things wiggle this way, and they wiggle back and forth, and they bend, kind of like that. And so all those things add up. Particularly when you have these very large molecules, their whole thing's just kind of in space until you get double bonds, triple bonds, where things start getting locked, having more of a locked conformation. Or you have cross-linking, where a molecule is large enough and it reaches over and then it actually bonds with itself or bonds with another molecule. So you have to worry about that. You remember that from polymers, the 22.5 we had to read? Okay. All right. We're not going to do that, so I don't want to. If you want to, you can talk about that.
Oh, it's a number.
There's a number. Don't worry about it.
What's the A with the circle on top?
Angstrom. Angstrom. So that's a measurement. It's to the minus 10th. It's the diameter of a atom, a hydrogen atom. So this is to the minus 10th, and that's the minus 12th.
Oh,
Angstrom, yeah.
okay.
It was more than a minute, but okay. Good?
He's a bragger for
Frog.
All right, let's talk about some crystalline solids. This is more stuff you do actually need to keep track of. We got ionic solids, molecular solids, and atomic solids. And so ionic solids have ions at the lattice points. Oh, good. Should be like right there, right? Molecular solids have discrete covalently bonded molecules at the lattice point. So the molecule itself, the whole molecule, is at the lattice point. And then atomic solids have individual atoms. So that's like your aluminum and your gold and uranium. Okay, those are individual atoms at the points. So those are our different solids here. So ionic, molecular, and atomic. And again, we've been through ionic. You guys, we learned this last year. We all know about ionic solids. Good? So here's some. We've talked about this three-dimensional little structure of carbon. We've talked about salt, sodium chloride. You can see how these arrange themselves in these repeating ionic structures. And then this is ice. This is what's going on when water bonds. And you can see these hydrogen bonds, again, these dashed lines indicating hydrogen bonds. Solid lines are indicating what kind of bonds?
What?
All right.
Solid lines?
These lines versus these lines. What are these? What is it? Hydrogen bonding. What is that? That line pointing to.
Ionic bond. That's London dispersion. Ion dipole.
We're talking whether or not it's molecular bond or
I don't know what it means. Oh. B.
B is what?
Bond.
Hydrogen bonding. What is A?
Hydrogen.
oh my god, it is
Bond. It's just a bond.
What kind?
Intermolecular force.
are we talking about a molecular
Intra.
Intra. Intra.
Intramolecular bond.
Oh.
Just say it.
It's intra.
Okay. When oxygen and hydrogen bond, we call that what kind of a bond?
Polar. No.
Molecular.
Polar what?
Polar covalent.
Covalent. Thank you very much. This is a covalent bond. Okay? Electrons are being shared between oxygen and hydrogen, although they want to spend more of their time around oxygen. He got the latest PlayStation 5 at his house. Everybody wants to hang out there. Okay?
We knew that.
You knew that. Yeah, I was just asking what kind of bond that is. So it's really important. You'll see a question like that on this test, your AP test, probably every test going forward. I need you to be able to see the difference between intermolecular forces and intramolecular forces.
Sp2 hybridization.
What is?
That.
What? What? Which one?
Oh no, one.
Oxygen. Oxygen is Sp2 hybridized.
Here you just.
Okay?
That's a bent.
That's a bent structure. What's going on there?
109.5.
How many pi bonds?
None. Zero.
Zero. How many sigma bonds?
Two.
2. There we go. All right.
Yeah.
Good. Good.
It's less than 109.5 degrees.
It is less than 109.5.
That has 2 lessons.
That question came up.
That means
What's the angle of a tetrahedral? Right? 109.5.
Where's the seesaw at?
Okay.
Seesaw?
Could be, but it's not.
Two, three, four.
This would need to be a.
Lone pair.
If this was a lone pair, you'd have your little triagonal bipyramidal, right?
Sure.
I guess.
This is,
Square plane.
well, the shape is square planar. The electron geometry is octahedral. Good deal. All right. Let's see. Classification of atomic solids. We've got metallic. You're going to know that. Network. And then this weird special case of group 8A solids. These guys are weirdos. They just like to hang out by themselves. We can convince them, like we do with xenon tetrafluoride, we can convince them to be with others, but, you know, they really just assume to be by themselves.
Are they noble metals?
They're what?
No.
The noble gases, they're weird.
Yeah, they're noble gases. They really don't need to be around each other, so their only attraction they have to each other is London dispersion forces. Now, when you can make something like xenon tetrafluoride like that, right, square planar shape, you can then start doing some different things. But all by themselves, you just got to get them really cold. And finally, London dispersion forces will take over and they'll stick together. All right, so closest packing arrangement, characterized by layers of uniform hard spheres that efficiently use space. So imagine you've got a bunch of small marbles and you just stack them together as best you can. You keep kind of gently shaking it until they settle into that as close as they can get. So that's closest packing. I don't really want to dig into ABA and ABC. It's not really that important. You just kind of need to know, are they next to each other? Are they like this? Right? That's what we're talking about. Minimize this use of space. Now, there are a couple different ways they can stack. But the idea here is these guys are all going to get together as close as they can. All right, where's my eraser? That's all we're talking about. And again, you got some pretty pictures in the book you can take a look at.
I just realized it isn't cold in here today.
What's that?
It isn't cold in here today.
No, it's fine. It's, yeah, it's 72 F word. So
That is so crazy. I never thought the day would come.
there you go. So this is what we're talking about, the different stacking. But again, you can see that layer after layer overlaps each other. Okay. And then you can, again, I'm not going to dig into these pictures here, just to understand that they're, again, pretend they're marbles stacked as close as they are. And then there's your ABC arrangement. So then there's cubic closest packing. That's what your unit cells look like. Nearest neighbor, this is where I've got a sphere in the middle. I don't want you to worry too much about this. All right, I want you to think about this briefly, though. How many spheres are in, yeah, question? You can put some tape over your eyes.
Is that clear tape?
All right, so the net number of spheres, you just do the math here, right? Each one of these, okay? Each one of these is 8, okay? Okay,
Oh,
Okay, yeah.
okay.
Okay. Right, I got a sphere here. If I look down on it, I'm going to cut it this way. And I'm also cutting it in the middle. So each corner is an 1/8.
And each face is.
Each face is a half. So in this one where I've got a face-centered cubic, I've got 6 half faces and 8 eighth faces, or 8 eighth spheres. Okay? That's all. Just to be able to mentally think how much is within a unit cell. So if I was to tell you the aluminum, for example, you could have told me how many aluminum atoms were in that. Okay? All right, there we go. We're not going to do that. You're welcome to, it's a fun little problem to think about. We can think about the radius of an atom being 144 picometers and use that to calculate the density of solid silver. And we would do that, okay? We would know the volume See, in your aluminum foil, you knew the volume, you knew the density, you knew how many atoms you had, and if you considered the stacking, you could actually get really close. There's some better ways, easier ways, but you could have used the cubic stacking to figure out a more exact method to calculate the density there. All right, so we can do that. Number of atoms, and there's your diagonals. Right, you remember the diagonals of a cube. You remember diagonals of a cube? No? Okay, well, it's okay. And we do this. I'm going to click through this. Again, this is all in your book.
It's like pre-cal.
It does look very pretty now.
Yeah, just baby stuff. Just baby stuff. We're okay. Okay. So r squared over 8, and r is 144 picometers. So 144 times square root of 8, which is 2 point something, 2.2, right? Is that right? Square root of 8. What's square root of 8? Y'all know it?
2/2.
Can you do that in your head?
Two what?
Not
That's
really
square root of 8.
memorized.
Oh, yeah.
Someone just say 2.2.
Okay. All right. So about 407 picometers. Okay, plug this. Whoops, there we go. The volume of the unit cell is d cubed. So that's 407 cubed. So that comes up to this number. We're going to reconvert to cubic centimeters. So the volume of the cell is 6.74 times 10 to the minus 23rd centimeters cubed. And we know the net number of atoms is 4. I got 4 silver atoms in a particular volume. And there's my density. 4 atoms at 107.9 grams per mole. Of course, we do all this blah, blah, blah that you can do. Avogadros. I'm glad you remembered something from last year. Okay. And then I've got 10.6 grams per centimeters cubed. And that's what you'd end up with. That's the density of silver. Is that more or less than aluminum?
I think so, yeah. I think it's more than.
Yeah. Okay. All right, y'all good? Let's now talk a little bit about bonding models for metals. So I've got to think about these properties that we've learned about metals, I guess, back when we were in 5th grade, and we learned it again when we were in 8th grade. We talked about metals as being malleable, as being ductile, as being conductors. One of the other words we use is lustrous, a fancy Nancy word for what? Shiny, right? And so malleable means I can take a hammer and smash on it and it doesn't explode and fly apart like hard crystals might. Ductile means I can draw it out into wires. And it's this bonding metal. And we talk about that's because of what's running around all these nuclei. Metals are swimming in a sea of electrons. There we go, good answer. There's a sea of electrons. Y'all remember the sea of electrons, right? The valence electrons are not localized to any one nucleus or nuclear core. They're moving around. Well, they're in electron clouds, but these electrons are freely flowing around the nuclei with the core electrons. So iron 2, for example, or iron, if I had a pile of iron here, I'd have a bunch of iron 2 cores and 2 electrons moving between them. So there we go. Speaking of which, there's our electron sea model. This is a regular array of metal cations in a sea of valence. There we go. There's a picture coming next. These mobile electrons are what conducts heat and electricity. These metal ions, as I hammer it, these metal ions simply move around and hold the cations together. That's different than if I had, say, a block of sodium chloride and I hit that with a hammer. What happens? It breaks. And why does it break? There's no free roaming electrons. The electrons are all locked. And if I have a positive and a negative, right, and they're attracting, so they're sticking together, and I hit it with a hammer and I move them, so the positives are now aligned with the negatives, they're going to do what? the positives and the negatives are going to repel, right? So if I start out like this, negative, positive, and then over here I've got a positive and a negative, a positive and a negative, right? These guys are all happy, right? Okay. Now imagine I take this and I hit it with a hammer right here, and I shift it. And so now I have positive, negative, positive, negative. What happens?
Fly apart.
They fly apart. They repel. These guys are going to repel, and these guys are going to repel, and these guys are going to repel. And they're going to break apart. If I hit, however, a piece of iron with a hammer, it just kind of mushes. Because the cations get moved, the electrons adjust and move around them while holding them together. And they also have to do with conducting heat and electricity. So let's look at this. Here's our alkali metal with one valence electron. This is your sodium, potassium, and stuff. And then there's an alkaline earth metal, your +2, or it could be iron, it could be other things. But I can imagine if I have this and I hit it and I move these cations down, everybody kind of adjusts, and then the electrons. In order to conduct electricity, all I do is I take here and I push an electron in. And if I put an electron in on this side, what has to pop out here to keep it balanced? I got to pop an electron out on this side to keep it balanced. This is what's going on in the wires and the plugs and electricity and the computers. I've generated an electron somewhere. I'm pushing them in one side, and therefore on the other side another electron has to pop out. Same fundamental things working with heat is I'm exciting some things. These things are moving about, and it's going to easily move about on the other side. Make sense now? You understand how wires work. All right, so we've got band models or molecular orbital models. We're going to assume them to travel around in molecular orbitals formed from the valence electrons of the metal atoms. And so I don't really want to dig too much into this. I just want to show you what's going on here. That if I had just two, we'd have two interacting. But if I have 6.0 times 10 to the 23rd, you create this whole band of interacting atomic orbitals. If I have a mole of something, then I've got a whole mess. And so this creates a solid level of interaction here. Okay? You can actually look at these if you wanted to. You can talk about empty molecular orbitals, those guys up top, and the ones that are filled that allow for the bonding to take place. We're not going to dig too much into that. This is kind of a, okay? I do want to talk about alloys. We may have even had this on a test, I think.
I remember that. Yeah.
Yeah, we talk about alloys. We have substitutional alloys and interstitial alloys. Cool. Okay. Apparently wasn't that important. All right. So, substitutional alloys. If I have a crystal, oh, there's actually a pretty picture coming up. Let's be easier. So, substitutional alloys, as the word says, I'm going to take a piece out and put something in its place. Interstitial alloys, I'm going to stick a little something, typically carbon, in the middle, in those gaps. Okay? So if I have big circles, and I know the pretty picture's still coming. Or if I have big circles like this, I can put a little atom right here. But imagine what that does if I have a little atom here, and I'm used to being able to move these around. That little atom's going to do what? going to kind of hold everything together. It's going to stiffen things up. And in fact, that's what we do when we make steel. We add a little bit of carbon into the iron, because the iron, I can beat on iron, and it just spreads out. I can pull on it and whatever. Once I put a little carbon in it, it gets stiff. Yeah.
How do you put the carbon in there, though?
Well, lots of different ways, but that's what blacksmiths were doing for years before we understood what was going on. The heating, cooling process, rubbing it in charcoal, folding it over, gets incorporated into things. Lots of different ways to do it now. Okay. Substitutional. Those can be things like some of y'all play instruments or make noise with instruments. Those things are made of what? Brass, yeah. Okay. So let's take a look at. Yeah. Copper and zinc. So if I look on the periodic table, copper and zinc are pretty close to each other, right? Yeah. We've all memorized it, right? So you know it, right? Just kidding. That's why AP Chemistry is the easiest class, because it gives you the cheat sheet with all the answers, right? You have the periodic table in front of you, so
So the periodic table
has all the answers. And a formula sheet too. So copper and zinc are pretty close to each other in size. They look different, right? Copper's got that wonderful light brown copper color, and we all know it. And then zinc is this bright, shiny, silvery type color. And yet they're right next to each other in the periodic table. Okay, so I'm going to take one of the copper atoms out, replace it with zinc. That's going to create a different property, the brass. Steel, where I got iron, what I was just talking about, and I'm dropping these little bits of carbon in it to resist the malleability, to make it stronger. If you have a low carbon blade, it's going to dull pretty quickly, because as I sharpen, it's not going to have a nice hard edge. Okay? So substitutional, I'm substituting something. Interstitial, I'm putting something into spaces. Yeah, so here's some interesting information. High carbon steel and mild. So if I'm making nails, I actually want nails to give a little bit. When I drive a big nail, I don't want it brittle. I want a little give. I want a little flex. Not much, just a little bit. Same thing with cables and chains and things. And then I got your medium steel. High carbon steel, I don't want very much give. Okay? Tough and hard, right? Knives, when it says cutlery. Network solids. These are atomic solids that have directional covalent bonds. They tend to be brittle. They're not effective. Why? They're not effective conductors. Why? Uh-huh. Well, okay. What are effective conductors? Why do we have a thing? Why are metals effective conductors? Sea of electrons. We call those mobile electrons, right? So why do you think these are ineffective conductors? What'd you say? Yeah, well, there's no sea, right? They're atomic solids. There's no mobile electrons. And it's the same reason that salts, these mobile electrons, the same reason that salts, if they're solid salt, they don't conduct electricity, but you put them in water and we call them what? Electrolytes. And electrolytes conduct electricity. And they do that because once they're in water, the ions are now mobile. Okay? All right. So these are ineffective, and that's why. Diamond. All right. We'll be talking about diamonds. Diamonds are real fun. So in this case, every diamond is surrounded by a tetrahedral arrangement of other carbons. Let's see if I can find my diamond. Yeah. Nope, that's not one. Here we go. There's a diamond. So, yeah, so here's what you got. I've got, yeah, right. Imagine, instead of this, that I've got a repeating structure of this, where at the end of this is a carbon that's got the same structure. Every one of these is connected to another one of these, and we have this repeating tetrahedral structure. That is a diamond. We talked about this last class, that we've got carbon all by itself is pretty much worthless, only worth to be burned up. You can think about like in charcoal. Okay. Now, once you get a two-dimensional structure going on, if you get the planar bonds and you got these nice two-dimensional structures, carbon starts having some use. Some of y'all actually use that type of carbon on a fairly regular basis.
Graphite.
That's graphite. But then if I take that two-dimensional structure and then I have a three-dimensional structure with it, it suddenly has some value to it. Society puts a lot of value on a diamond that has, or a carbon that has three-dimensional bonds to other carbons. Okay. These covalent bonds are resulting from overlapping Sp2 hybridized carbon atomic orbitals. All right. And because it's Sp2 hybridized, remember, if it's Sp2 hybridized, how many pi bonds does it have?
0. Well, it could have
If it's Sp2 hybridized, how many pi bonds can it have?
0.
How much can it have?
0.
0, because
All single bonds.
all single bonds, right? Good. And if it's all sigma bonds, then we get to use the localized electron model.
Right.
We only need the molecular orbital model when we start talking about pi bonds to account for the fact that those electrons are not localized. Good. So this is what it looks like. I mean, that's what diamonds look like.
All I see is the cathedral.
So yeah, so you see all this repeating tetrahedral. So here's one,
Yeah.
there's one, except it just goes off the side. There's another one that goes to the back. Okay. A large gap between the filled and empty levels. Electron transfer is difficult.
That's a lot of pressure.
Diamond is not going to be a good electrical conductor because all of those electrons are locked up. It's not going to have any free electrons to conduct. You can cut with them, whatever. And if you want to, you can actually,
Make your own diamond.
yes, you can make your own diamond. Yeah,
How long does it take? Is it like, bam?
Probably has been done.
a little while.
Is there a YouTube video from that?
There it is. Yeah, but we do.
Survive
So
that amount of pressure.
150,000 atmospheres and about 2,800 degrees Celsius, you can just make your own diamond.
How does that just happen? I don't understand.
Well, it doesn't just happen. You make it in the lab. So,
A lab with a very strong material, I assume.
yeah.
What is graphene?
It's related to that. You can look up the structure. It's sheets of it.
So what differentiates it from graphite?
I'm not sure exactly how the layers interlock, how they're different. But yeah, so you can actually make your own. It actually turns out to be more expensive than mining at this point. But there are some applications where you need an because natural diamonds are going to have occlusions in them. Going to have little imperfections where other stuff gets trapped in there, and you suddenly don't have this area doesn't have a nice clean bond, and so something gets in there, some imperfection. But sometimes you need a really nice, pure diamond for some particular application, and so they'll have to make those.
What material survives that pressure?
Graphite.
Lots of stuff.
Not many.
Okay. So here's what we're looking at, and I don't really need you to dig into that. I just want you to kind of think about it. So graphite is slippery, black. It's a conductor of heat and electricity. Both carbon, both have bonds. Okay. The structure is layers of carbon in a fused 6-membered rings. We talked about 6-membered rings last class, right? Those benzene rings.
Oh, yeah.
But these are not benzene, but these repeating structures of 6-membered rings, because we're not having double bonds. They're against each other. Is there a picture? No, I don't know. All right. So you can have this, and then let's see if I'm going to do this right. Probably not. Like this, right?
Watching an entire video describing
Imagine that. What's that?
I remember watching an entire video just based off of why it's always 6.
Yeah, it's kind of good stuff.
Because it's just the most structurally stable.
Yep. All right, so we're surrounded by 3 other carbon atoms. So those carbon atoms are going to be what hybridized?
Sp2.
Sp2 hybridized.
Why?
There's 3 surrounding. Instead of 4 surrounding like diamond, diamond's all Sp3 hybridized. These are Sp2 hybridized. Because again, I can look at this terrible artwork that I did. Okay. And let's see, we're going to do this one. Okay. Notice this carbon and this carbon. I've got 1, 2, 3 other carbons. 1, 2, 3 other carbons.
What's the symbol for carbon?
What?
Can you draw it, please?
Oh, okay. Do you just want to see what shape you can make fun of this time?
No, I like your C's.
And there, as we described just a few seconds ago, there's an Sp2 hybridization. 3 Sp2 orbitals on each carbon atom are going to form sigma bonds, and 3 other carbon atoms. This one remains unhybridized and perpendicular. So you remember, it's sheets of carbons. The S and 2 of the P's are hybridized, so it's Sp2 hybridized. And then I've got that P still left pointing up, perpendicular to the plane. Those electrons that are pointing up. This is what allows us to have slipperiness. Okay? 2-dimensional, very strong bonds. The third bonding is not very strong, and it slides. All right. There we go. There's this weak bonding between layers because of those overlapping bonds. So I've got these, remember these, they're not bonding with each other this way. They're creating a bond between those. Okay? But that's a very weak bond. And so they slide easily. Oh, there we go. So you can see nice little pretty pictures. Those are your p orbitals that are going up and down, and your pi bonding network. Yeah, we're going to stop at pi. Cool. All right. Cool. Questions? Good times?
When you break apart, let's say, salt, you know how you said it slides so the positives are matched up. So theoretically, if you match them exactly up, why don't they just stick back together?
Because the practice of breaking them is, that's how you break crystals, right? If you're working with any crystal, you put a chisel on it, pop it,
So why can't you just stick it back together?
because you can't get it all the way back together.
Because it jostles it around.
Because it's going to be uneven, and just getting it back together, yeah. Yeah.